All right. We left off yesterday. I had this list for sorted out when we're talking about means and when we're talking about proportions. And so I had this running list going of saying, when you're using proportions, make sure you're using the formulas for mean and standard deviation for proportions. And when we looked at examples with the means, make sure we're using examples for mean and standard deviation of the means. But a lot of the process on these problems are going to be the same as they were for proportions. They're just using different formulas for means and standard deviations. But there's going to be one other difference that we're going to talk about today. And that was, if you remember, when we talked about proportions, whether we could use a normal distribution relied on whether n times p and n times 1 minus p were both at least 10. In other words, the number of times the thing happened, we're expecting the thing to happen, and number of times we're expecting the thing not to happen are both at least 10. The idea is once we get a large enough sample, then we can use a normal distribution. It's going to be close enough to a normal distribution. Now that's going to be slightly different when we talk about means. The condition that we use is going to be different. It's actually going to be easier, but it's going to be different. And so one common mistake that people make is that they use the wrong condition for normality when they're going through and doing examples with means and proportions. It's one of the more common things to mix up. So that's what we're going to talk about today. Most population distributions are not normal distributions. So what if the shape isn't normal? As our sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and starts to look more and more like a normal distribution the larger a sample that we take. It starts to center at the mean and starts to look more and more like a normal distribution. And this fact is called the central limit theorem. If we draw a random sample from any population with a mean and standard deviation, central limit theorem says that when n is large, the sampling distribution of the sample mean is approximately normal. What do we mean by when n is large? The threshold we're going to use for how large n needs to be. So here's an example. The threshold we're going to use is for n to be at least 30. And so that is the test that we're going to use for means. If we want to know if a population distribution, if the sampling distribution is normal, the condition we need to check before we do the problem is going to be, is the sample size greater than or equal to 30? So when we're testing means, we're testing whether the sample size is at least 30. For proportions, we're testing whether n times p and n times 1 minus p are both at least 10. I will say it again. I will say it many, 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 many times before the AP test. For proportions, we're testing whether n times p and n times 1 minus p are both at least 10. If they are, then we can go ahead and use a normal distribution. If we're looking at means, all we need to do is check whether the sample size is at least 30. If it is, then we can assume that the distribution is approximately normal. But those are going to change when we're talking about proportions versus when we're talking about means. So the easy way to keep it straight is that proportions is the one with the proportion in it, right? You can't check n times p for a mean because there is no p. There's no proportion to check. So 30 is going to be our threshold, our baseline with which to check things.
For proportions to be normal, both of those need to be true?
Yes. So, yeah. we'll talk about that more in the next chapter. This will come up again in the next chapter, which is why I said we're going to go through this over and over again. So a lot of these ideas, the reason we're spending a lot of time is that a lot of these ideas are going to come back in chapter 8 and chapter 9 and chapter 10. A lot of the stuff in this semester ties together and is very connected. 2 slides down, 1 to go. Here we go. Let's do an example. Based on service records from the past year, the time in hours that a technician requires to complete preventative maintenance on air conditioner follows the distribution that is strongly right skewed, where the most likely outcomes are close to 0. Uh-oh, it's not a normal distribution. Well, that's too bad. Mean is 1, standard deviation is 1. Your company will service a simple random sample of 70 air conditioners. You have budgeted 1.1 hours per unit. Will this be enough? So what is the probability that we want to find here? Well, we want to find the probability that when we have our sample of 70, that the mean amount of time that we spend doesn't go over 1.1. Because if it doesn't go over 1.1, then we're in good shape. If it does, then we're in trouble. We haven't budgeted enough time. So the probability that we're finding is going to be cut off at 1.1. And 1.1 is our threshold. Did we go over it or not? We can still check whether the population is at least 10 times the sample size, which we talked about last week. And the other thing that we're going to check for is, will these samples of 70 follow a normal distribution? And what are we checking to see if we're following a normal distribution? We're checking whether our sample size is at least what? 30. Is our sample size at least 30? Yes, because our sample size here is 70. 70 is our n, our sample size here, which is at least 30. Mean is 1. Standard deviation, there's your formula for standard deviation. It's going to be the standard deviation over the square root of n. Since n is 70, we're going to use 1 over the square root of 70. Since n is at least 30, we can use a normal distribution. So now we can draw our picture. So go ahead and take a minute and draw the normal curve so you can get a visual of where the 1.1 that we're interested in finding the probability of, where that 1.1 is going to be. Remember, when you draw the picture of the normal curve, usually you want to use 2 standard deviations on either side. You want to label 2 standard deviations on either side. So I'll give you a moment to see if you can draw that picture before I go through and show what it looks like. Give me 2 standard deviations on the other side. That's 1 standard deviation on each side. There you go. Center of the curve should be at 1 because the mean is 1. And then you should basically be scaling by 0.12s on either side. And I want you to mark where 1.1 is on the curve that you just drew. And there's a lot of things that are helpful in drawing this picture. It can give you a sense of what the distribution is that we're looking at. It can give you, if we're shading areas, it can give you an idea of whether the final answer you get for the percentage is a reasonable percentage. It can give you an idea if you're calculating the z-score of about where the z-score should be. Because you'll notice 1.1, you labeled it right underneath your 1.12. So that means your z-score should be a little bit less than 1. If you want to go ahead and do your normal CDF, then go ahead and do that. I have drawn the picture. Look at my beautiful artwork that is mine, that I drew. I even did 3 standard deviations. I'm that extra, as you would say. Left to right, 0.64, 0.76, 0.88, 1, 1.12, 1.24, 1.36. If you just did 2 standard deviations, it should start at 0.76, then 0.88, and then 1, 1.12, 1.24. We're counting by 0.12s on either side. And there's the area. This is the bad zone. This is the zone where we didn't budget enough time. You can do your normal CDF. If you want to compute your z-score, there's your z-score. Again, a little bit less than 1 is my z-score. 0.2033 is the percentage that is in the bad zone. About a 20% chance that the technicians will not complete the work within the budgeted time. Anyone need help with the normal distribution work? And getting the z-score, getting the normal CDF?
I just have a question. What would be the purpose of getting to the z-score if we only need the chance that the technicians will not complete the work within the budgeted time?
So, okay, this is a question about like what work do you need to show, which I'll talk a lot more about once we do and go through the start looking at more free responses. You need to, in some way, show that you're doing a normal distribution calculation. And so one of the ways you can do that is with a picture that's labeled with the 2 standard deviations on either side. One of the ways you can do that is by computing a z-score. That will show the distribution you're looking at. One of the other ways is to write out, we are using a normal distribution with a mean of this and a standard deviation of this. And so basically, a z-score calculation is one of the ways that you can get credit for showing the proper amount of work. Another way is by drawing a picture. And when we start to look at scoring rubrics, we'll talk a lot more about that in detail.
So drawing this would give you credit for your work?
I would say that, plus writing down the normal CDF that you put in the calculator, like verbatim, would give you full credit.
Like, would I compare along with the picture? Or would you want us to explain what every value meant?
That would be fine, I think. Yes. Again, I'll answer a lot more of those kind of questions when we start to get into like April and start really looking at free responses and how they're graded and what the specific scoring rubric for this specific question is. Anyone not sure how to do some part of this calculation and not sure how to get the 0.2? All right. Then that only leaves one thing. Homework. There it is. So we have this. That should be all the book assignments. I also have the review, which I'll hand out to you in just a moment. And if you're not here today, then I'll hand it out to you tomorrow. And we will tomorrow start going through some practice problems on this section and some more examples.